Imagine a single space rock containing enough platinum to make every person on Earth a billionaire. Not some far-off dream, but a tantalizing reality floating in our cosmic backyard. Asteroid mining, humanity's next giant leap, whispered about in science fiction, now teeters on the precipice of industrialization. But is this a monumental delusion, a fool's errand costing trillions with no return, or the inevitable future that will fuel humanity's expansion into the stars and fundamentally transform our entire economy? The answer might surprise you. Welcome to Orbital Arc, where we cut through the hype and dive deep into the economics and engineering of humanity's next giant leaps. We explore the profound implications of pushing the boundaries of what's possible, challenging conventional wisdom, and unearthing the true potential of our future. Today, we're unraveling the complex truth behind asteroid mining. We'll explore the tantalizing promises of unimaginable wealth, the staggering technological and financial hurdles that threaten to ground our ambitions, and ultimately, whether these space rocks truly hold the key to an unprecedented era of wealth, freedom from Earth's finite resources, and true space industrialization. Prepare to have your perceptions challenged and join us as we chart the course for humanity's off-world destiny. So, what treasure trove awaits us out there, sparking such a galactic fever? For centuries, humanity has gazed at the stars with wonder, but now a select few look with dollar signs in their eyes, and for good reason. The sheer potential wealth locked within the asteroid belt is truly mind-boggling. Asteroids are primarily classified into three types: C-type, rich in water ice and organic compounds; S-type, stony asteroids containing iron, nickel, and various metals; and M-type, dense with precious metals like iron, nickel, cobalt, and most importantly, platinum group metals. These PGMs, platinum, palladium, rhodium, iridium, osmium, and ruthenium, are not just luxury items. They are indispensable for modern electronics, critical components for catalytic converters in nearly every vehicle, and essential for hydrogen fuel cells that promise a clean energy future. Beyond PGMs, rare earth elements, vital for high-tech devices from smartphones to missile guidance systems, are also believed to be abundant. Iron, nickel, and cobalt, while common on Earth, are fundamental building blocks for future space infrastructure, eliminating the need to launch them from Earth's deep gravity well. Some conservative estimates suggest a single M-type asteroid, just a few hundred meters across, could contain enough platinum to make every person on Earth a billionaire. This abundance, if accessible, wouldn't just enrich humanity. It could shatter terrestrial commodity markets and fuel an entirely new space-based economy, moving us beyond Earth's finite, dwindling resources into an age of cosmic plenty. But how do we even begin to grasp such riches? The technological challenges are immense, bordering on the fantastical. First, asteroids are millions of miles away, constantly moving through the void, demanding incredibly sophisticated, precise, and highly autonomous propulsion systems. Think advanced ion drives or even future nuclear propulsion for multi-year missions just to reach them. Once there, the environment is unforgiving. Extreme temperature swings from hundreds of degrees below zero to scorching heat, a near-perfect vacuum, and the perplexing realm of microgravity. Mining operations here are nothing like Earth. They require entirely new techniques for drilling and excavating without gravity, preventing material from simply floating away, and separating elements in zero-G with unprecedented efficiency. This necessitates highly autonomous robotics, capable of identifying, extracting, processing, and refining materials with minimal human intervention due to communication lag that can stretch for minutes or even hours. We're talking about entire self-sufficient factories in space, equipped with advanced AI, long-duration reliable power sources, and innovative material handling systems, all built, tested, and proven in space's profoundly hostile environment. It's a grand engineering puzzle, demanding innovation across every scientific discipline. Beyond the engineering marvels, the economic realities cast a long, cold shadow. Launching even a kilogram of payload into space still costs thousands, if not tens of thousands, of dollars. Developing and deploying asteroid mining missions requires hundreds of billions, if not trillions, in initial investment. dwarfing even the largest terrestrial mining projects. The financial risks are colossal, with ROI timelines stretching decades into the future, fraught with technical, operational, and market uncertainties. Consider the infamous glut problem. If you manage to bring back a significant amount of platinum to Earth, its market value, currently driven by scarcity, could crash from a sudden influx. What was once a multi-trillion-dollar asset could overnight turn into a mere fraction of that value. This scenario, reminiscent of historical commodity market collapses like the diamond market's careful control, is a critical hurdle for any earthbound resource extraction model. The real economic driver, therefore, might not be about enriching Earth's markets. Instead, it could be about using materials in space to build humanity's off-world presence, entirely bypassing terrestrial market sensitivity. This fundamentally shifts the focus from a high-risk commodity play to an essential infrastructure play, enabling future space endeavors and creating an entirely new, self-sustaining economy beyond our planet. And what is this true gold that fuels an in-space economy? Surprisingly, many experts agree it isn't platinum for terrestrial markets, but rather water for space. Water ice, abundant on C-type asteroids and within permanently shadowed lunar craters, can be processed into its constituent parts. Hydrogen and oxygen, the most efficient chemical rocket fuel known. Imagine a network of orbital refueling stations strategically placed throughout the solar system, allowing spacecraft to travel further and faster without having to lift all their fuel from Earth's deep gravity well. This drastically reduces launch mass and cost for deep space missions to Mars, the outer planets, or even interstellar probes. Beyond propellant, water is the elixir of life, essential for life support in space habitats, providing breathable air, drinking water, and crucial radiation shielding. A sustainable, locally sourced supply of water would drastically reduce space exploration and colonization costs, making lunar bases, Mars missions, and large-scale orbital manufacturing not just feasible, but economically viable. If humanity can truly live off the land, using resources for fuel, advanced construction, via 3D printing of metals and plastics, closed-loop agriculture systems, and thermal management, the entire paradigm of space industrialization changes, making humanity truly self-sufficient and permanently off-world. But even if the technology and economics align, a complex legal and geopolitical maze exists, often likened to the Wild West of space. The Outer Space Treaty of 1967, the cornerstone of international space law, explicitly states that outer space, including the moon and other celestial bodies, is not subject to national appropriation by claim of sovereignty, by means of use or occupation, or by any other means. But here's the billion-dollar question. Does this prohibition apply to extracted resources? Who owns these celestial bodies? Who regulates mining for safety, environmental impact, and potential harm? What about due regard for other nations' assets or scientific missions? Nations like the United States, with the Space Act of 2015, and Luxembourg have unilaterally granted property rights to extracted space resources for their citizens and corporations. However, these national laws are not internationally recognized, creating profound ambiguity and the potential for serious disputes. This critical lack of a clear, internationally agreed-upon legal framework, potentially guided by principles like the common heritage of mankind, creates immense uncertainty and could lead to conflicts among nations and corporations vying for these extraterrestrial riches. Establishing a robust, multilateral regulatory regime is paramount to prevent a chaotic and dangerous space gold rush, ensuring equitable access and responsible stewardship of the cosmos. Despite these monumental challenges, the very idea of asteroid mining continues to inspire unparalleled innovation and relentless pursuit. Early pioneering ventures like planetary resources and deep space industries laid crucial groundwork, even though their eventual failures taught valuable, albeit expensive, lessons about immense capital requirements, technological immaturity, and the critical absence of a viable market for their proposed services. Today, the landscape is maturing. Companies like Astroforge are taking a more pragmatic approach, aiming to refine materials in space for in-space utilization, rather than the vastly more expensive and market-disrupting proposition of bringing raw ore back to Earth. Their missions are smaller, more frequent, and designed specifically to test key technologies. Public organizations like the European Space Agency, ESA, NASA, and JAXA are heavily investing in in-situ resource utilization, ISRU research, specifically for sustainable lunar and Martian exploration. The overarching strategy is definitively shifting from a speculative space gold rush for Earth to a more sustainable long-term vision of building a robust space economy from space resources. A profound and necessary evolution reflecting a maturing, more realistic approach to humanity's cosmic future. So, where does that leave us in this cosmic debate? Is asteroid mining a billionaire's delusion or the future's gold rush? The answer is nuanced, yet profoundly optimistic. It is definitively not a delusion. The resources and their potential are undeniably real and vast. However, it is also not the quick terrestrial gold rush many initially envisioned. Instead, it is a long-term, multi-generational endeavor demanding unprecedented technological advancements, immense capital investment, and the establishment of a new, universally accepted international framework for space commerce. It's less about immediate terrestrial riches and more about building the foundational infrastructure for humanity to truly become a multi-planetary species, unshackled from the limitations of Earth. The resources exist, human expertise continues to grow exponentially, and the insatiable desire to expand beyond Earth is more potent than ever. Yet harnessing these extraordinary resources will undoubtedly be one of humanity's most challenging, complex, and ultimately transformative undertakings. It's an undertaking that will pave the way for a self-sufficient space economy, liberating us from terrestrial constraints and propelling us towards an expansive, limitless future among the stars. The truth about asteroid mining is that it represents both an immense challenge and an even greater civilization-altering opportunity. It's not a short-term gamble for quick profit on Earth, but a long-term strategic investment in humanity's future beyond Earth, unlocking resources crucial for expansive space exploration and robust industrialization. While it might seem like a billion-dollar delusion if viewed through the narrow lens of immediate terrestrial commodity markets, it is undeniably the future gold rush for building a thriving, self-sustaining civilization in space, opening up boundless possibilities for our species to thrive among the cosmos. What are your thoughts on humanity's audacious quest to mine the heavens and establish a permanent presence off-world? Do you believe the challenges are too great, or is the reward truly worth the effort? Let us know your perspectives in the comments below. If you found this deep dive insightful and thought-provoking, make sure to like this video and subscribe to Orbital Arc for more explorations into the fascinating future of space industrialization and economy. Until next time, keep looking up and dreaming big.